Okay, so you have seen transformations before. You take a vector x. Okay, let me get the little thing here. You take a vector x, you multiply it by a matrix A, and you get a transformation. You could take a vector and rotate it. You could take a vector and reflect it about an axis, okay, by multiplying by an appropriate matrix A. Well, all right, in this section, we're going to talk about special vectors on which the action of A is quite simple. Okay, so in example one here, all right, what we have is we have a matrix A, which it has values 3, -2, 1, and 0, and we have two vectors, a vector u and a vector v. And if you take the matrix A and multiply it by the vector u, which is -1, 1, okay, and actually, you might, let me just, on paper, multiply that. I mean, I can see from the graph in figure 1 what it should be. The graph is telling me that when I multiply the vector u by the matrix A, what should that vector equal based on the graph? What should the coordinates be? Who can tell me from figure 1? What's the transformation on the vector u? The vector u gets transformed into the vector a times u. Well, based on figure 1, okay, that's right, Ben. The coordinates are -5 and -1 for that vector a times u. And if you multiply matrix A times the vector u on your paper, you'll see that's -5, -1. Okay, cool, no problem there. Now let's look at vector v. Vector v is the vector 2, 1, and if we multiply the vector 2, 1 by the matrix A, okay, that vector AV, well, what is that vector AV based on the picture in figure 1? What is that equal to? What vector does vector v get transformed into? Okay, based on the picture. Well, what is A times V? What does A times V equal? That's right, Hung. That's right, Marvelous. For the vector 4, 2. And in the picture, you can see that A times V is at 4, 2. So what's interesting about this vector V is when we multiply it by A, it's I want to say this the right way. Well, A times V is just equal to some multiple of V, right? A times V equals what multiple of vector V based on the picture? And it might be a little hint if you read it there. Thank you, Olivia. A times V is just 2 times V. A times V is just 2 times V. So the matrix A stretches or dilates the vector V. Okay, and we call the matrix A, well, we call the vector V an eigenvector of A. Okay, in other words, yeah, the vector V is an eigenvector of A, and the value of 2 is an eigenvalue of the matrix A. Okay, so the effect of multiplying an eigenvector by a matrix A is just to stretch or dilate that eigenvector. Okay, this action is very important in mathematics. It's actually amazing how important it is. Now, I'll comment here, you've already actually seen this, okay, because if you remember the steady state vector Q, if you take the matrix A, which is a stochastic matrix, let's say, I mean, this is like section 4.9 now, this little example they talk about. If A is a stochastic matrix, the steady state vector Q, okay, the steady state vector Q for A satisfies the equation AX equals X. In other words, A times Q equals 1 times Q. So the steady state vector Q is actually an eigenvector of the matrix A, corresponding to an eigenvalue of lambda equals 1. All right. But we want a formal definition here. We want a little more formal definition for what an eigenvector and eigenvalue is. We've seen a few examples. Well, here's a definition right here in section 5.1. An eigenvector of an n by n matrix A, and we have to be talking square matrices, okay, for eigenvectors and eigenvalues. An eigenvector of an n by n matrix A is a non-zero vector X, non-zero vector X, such that A times X equals lambda times X for some scalar lambda. The scalar lambda is called an eigenvalue of A if there's a non-trivial solution of X of A times X equals lambda X. The vector X is called your eigenvector corresponding to eigenvalue lambda. Okay, so for example, in example 2 here, they have a matrix A and they have vectors U and V, and they're asking, are vectors U and V eigenvectors of A? Are the vectors U and V eigenvectors of A? Well, to check, like you'll see in here, they multiply A times U, and they get negative 24, 20 as the vector. Okay, they get that. That's fine. And but negative 24, 20, that vector happens to equal negative 4 times the vector U, which is negative 4 times U. So therefore, the vector U is an eigenvector, and negative 4 is the corresponding eigenvalue. Okay, are there any questions on that? All right. Well, if not, let's move forward then. Let's move forward. If we take the vector A times V, if we multiply vector V by A, we're going to get negative 9 and 11. Okay, but there's no multiple of 3 and negative 2 that would give you negative 9 and 11. So that means that the vector V is not an eigenvector of A, because A times V is not a multiple of V. Okay. All right, so this is good. Yeah, and then they have a picture here on the left. They have a nice picture in on the left here, showing that how A times U just stretches the vector U, and very good. So okay, this is nice. This is nice, but of course, you know what? Like here, they have that matrix A in example 2, and they're giving you some vectors. And hey, it turns out the vector U is an eigenvector. Okay, but you know, how did they get that? I mean, I think don't you want to know how we get the eigenvectors? I mean, I think that's pretty important, right? So let's go to an example here then. Let's go to an example that I have. Are there any questions on example 2 before we move on? Who's feeling comfortable? Who's feeling comfortable? Maybe give me a thumbs up if you're feeling good. Okay. All right. Thank you, Benjamin. Olivia Hung. Very good. Very good. Well, let's move forward then. Let's move forward. Okay. Okay. Here is a matrix A. Okay, this is a 3x3 matrix. And you're being told that one of the eigenvalues is lambda equals 2. Now there could be multiple eigenvalues. There could be up to 3 eigenvalues here because it's a 3x3 matrix. But right now, one thing at a time. I'm going to show you how to find eigenvectors if you're given an eigenvalue. And then in section 5.2, I'll show you how to find the eigenvalues. But an eigenvalue of A is lambda equals 2. We want to find a basis for the corresponding eigenspace. Okay, the eigenspace is the space of eigenvectors corresponding to the eigenvalue. Let me give you a moment to copy this example down. Okay, so once again, we want to find a basis for the eigenspace corresponding to the eigenvalue lambda equals 2. So remember what the definition of an eigenvector is. If you have A times X, and that equals lambda times X, okay, where the vector X is non-zero, okay, then you have an eigenvector. The vector X would be an eigenvector. So that being said, that's where we need to start. If we're going to find the eigenspace, which is the set of eigenvectors corresponding to this eigenvalue of 2, well, we need to start with the definition. So let me go to the next page here, and we're looking for non-zero vectors X, such that A times X equals lambda times X. Lambda, remember, is a scalar. Okay, so how are we going to find these eigenvectors? Well, if A times X equals lambda times X, I can write lambda times X as lambda times the identity times X, because what is the identity times the vector X? That's just the vector X, right? That's just the vector X. Now, why would I want to do that? What do I gain by doing that? Well, I can certainly subtract lambda times I times X. I can subtract that vector over to the left side, and so of the equation. And so the right-hand side of the equation will be the zero vector. And so I have A times X minus lambda times I times X equals the zero vector. And then I can factor the X vector out. Okay, because it's a common vector. Now let me ask you, you see here in this step how I factored the X vector out on the right side. Okay, would it be okay to factor the vector X out on the left side? Could I do that? In other words, would this here be true also? Being that this is true, A minus lambda I, that matrix times the vector X equals the zero vector, would it also be true that the vector X times A minus lambda I equals the zero vector? I mean, in other words, what I'm saying is, can I factor the vector X out on the left side as opposed to the right side? Does it matter? Do I have to factor the vector X out on the right side here? Or can I factor it out on the left side? What do your instincts tell you? Okay. Well, your instincts are good. The answer is no. And it does matter. And it does matter, absolutely. But let me just say the answer is no. What's the reason? Notice here, you have a matrix in this step here. You have a matrix times a vector, but that is the matrix times a matrix, right? What's true about multiplication of when you multiply matrices? Matrix multiplication is not what? What? You can add matrices, you can subtract matrices of the same size. Well, I don't want to digress here. For some reason, I factored that. Okay, that's what I want, Matrix multiplication is not commutative. So, I mean, I cannot factor that vector X out on the left side here because it's on the right side. In other words, I mean, everybody's okay, I think, with this step here. Because the vector A times the vector X is A times X. And lambda times I times the vector X is lambda I times x. So this step's okay. But that doesn't mean then that the vector x times a minus lambda I would be that you could factor it that way. You can't, because the matrix multiplication is not commutative. Olivia, are you feeling a little better with that now? That explanation as to why we have to factor the vector x out on the right side and why it matters? Or Eleanor, I'm sorry. Yeah, or Olivia. Yeah. I want to make sure everybody's completely comfortable with this, and I appreciate all input in the chat room. You feeling a little more comfortable with that now, Olivia? Excellent. Okay. Well, all right. So, okay, well, how does this help us? Well, we have a system of equations that we can solve. We're going to solve this augmented matrix, A minus 2 lambda I in the zero vector. We're going to solve this homogeneous system of equations here. The identity, don't forget, the identity, and maybe I can use the other thing here. I'm so used to using the mouse. I got so good with it, you know, over time. Comfortable with it. But the identity matrix is this matrix. So when I have A minus 2 times the identity matrix, that's going to then equal what you see here, what I'm circling. Please let me know if you have any questions on that. Okay, and so this is my system. Wow, how about that? What's interesting about this system of equations? Or maybe I should ask, do you think, will there be free variables when I solve that system of equations? That's right, Eleanor. There are identical rows. So really, how many equations do I have here? How many equations do I have in my system? That's right, Haley. That's right, Hum. Just one. Just one. So one equation, and there's going to be two free variables. That's right. There are 3 variables total. 2 of them are going to be free. 3 variables, 1 constraint. That means you have 2 free variables. Okay, well let's continue and let's go ahead and solve for my eigenspace, my vector x. May I go to the next page? All right. Okay, are there any questions? All right. Well, so what I did then, of course, thank you, Eleanor, and thank you, Hung. So, of course, what I'm going to do is I'm going to take -1 times row 1. Let me try my stylus here. negative 1 times row 1 plus row 2, put the result in row 2. And then I'm going to take negative 1 times row 1 plus row 3, put the result in row 3. And therefore, you get this augmented matrix. X3 is free, X2 is free, and it turns out X1 is 1/2 X2 minus 3X3. And so what I do is I write my eigenvector X in parametric vector form. Okay? So that I can identify the basis for my eigenspace. Okay, so I have two vectors in my basis. And so I have my basis for the eigenspace. But what I did was I kept the negative 3, 0, 1. I kept that basis vector. But the 1/2, 1, 0, I just took a multiple of that. I got 1, 2, 0. What multiple am I taking? So 1/2, 1, 0. I'm going to instead replace that vector with 2, 1, 2, 0. How did I get the 1, 2, 0? That's right, Lewis. I multiplied by 2. So, basis, if you have basis vectors, if you take multiples of the basis vectors, that's okay. It doesn't change the basis. It doesn't change the basis. All you do when you take a multiple of a vector is you just dilate it or stretch it. The basis, the span of that vector is still the same as the span of the original vectors. So if you take multiples of your basis vectors so that you're able to get nice vectors with integers, those new vectors are just they're just multiples of the old vectors, and so those new vectors are just either take the old vectors, either shrink them or stretch them, right? That's what multiplying a scalar does to a vector. But shrinked or stretched vectors still are doesn't change the basis. It doesn't change what the basis is. It doesn't change the geometry. And as a matter of fact, they have a figure here, figure 3, in section 5.1. I'd like to show you a picture of this this basis. So I will do that if we're ready here. Are there any questions? All right. Well, let me go to the book then and show you the figure here. So this corresponds to example 4, the one that we did here, and I want to, yeah, we did example 4, okay, and there are, you know, the two basis vectors. And figure 3, the matrix A acts as a dilation on the eigenspace. Okay, so remember well, yeah, this is a two-dimensional eigenspace. So the two vectors, the 1, 2, 0 and the negative 3, 0, 1, form a two-dimensional eigenspace on figure 3 on the left. But if you were to take all the vectors in that eigenspace and multiply it by the matrix A, it would see how it stretches the vectors. It would stretch the vectors, or it could dilate the vectors too. But in this case, they're showing stretching the vectors. Well, no, it would stretch them. Because lambda equals 2, so it's going to stretch them by a factor of 2. And but it doesn't change the geometry of the eigenspace. It doesn't change it. It's still the same plane. Still the same plane. Okay. All right. Are there any questions on that? Okay. Well, let's go a little bit. Let's go forward here. There's a theorem in the book that you have not seen how to find eigenvalues yet for a matrix. You can see how to find eigenvectors, but you have to be given the eigenvalue in section 5.1. However, there is a theorem here, theorem 1, that says if you have a triangular matrix, okay, if you have a triangular matrix, the eigenvalues are simply the entries on the main diagonal. Okay, and that's going to be a little more obvious in the next when we get to section 5.2. Okay, so let's move forward here. Let's move forward. Now, you can have an eigenvalue of 0 for a matrix. That can happen. And that would happen when A times X equals 0 times X. If that, I want to be careful, that isn't quite right. If the vector equation A times X equals, no, I want to be careful here. Yeah, that is a vector equation. If you take A times X equals 0x, and the vector X has a non-trivial solution, then 0 would be an eigenvalue. But remember, this equation 4 above is equivalent to A times X equals 0. And that would only have a non-trivial solution if and only if A is not invertible. Okay, we can employ the invertible matrix theorem. Remember that? The invertible matrix theorem from section 2. I believe it's 2.3. Yeah. If you have A times X equals 0, and the vector, well, I want to say this the right way. Let me kind of refresh your memory on this. Hold on. Let me go to the whiteboard. So let's consider A times X equals the 0 vector. And our matrix A is n times n. Okay, well now, if an inverse exists, the vector x, and you know, so think now, you know, think of this, I want to say this the right way. Let me be a little more careful here. This is fine. So if an inverse exists, the vector x is going to equal A inverse times the zero vector. That's if an inverse exists. Well, what does A inverse times the zero vector have to equal, class? Okay, so we're assuming here that A inverse exists. If A inverse exists, then x equals A inverse times the zero vector, right? In other words, hold on, let me be a little more clear here. A times x, if the inverse exists, I can multiply the left side of that vector equation by A inverse. Okay, but what does A inverse times A equal? What does A inverse times A equal, class? Good. That's right, Hung, the identity. So the identity times the vector x is just x. And so the vector x will equal A inverse times the zero vector. But what would that equal? What would A inverse times the zero vector have to equal, class? That's right, Andres. It'd have to equal the zero vector. Okay, so the point is, for this vector equation, okay, for that vector equation, if A inverse exists, that implies that the only solution for x is the zero vector, right? That implies that. Okay. Well, if we go back to the book here, okay, if we go back to the book, all right, where they're talking about the zero vector, or the eigenvalue of zero. Zero is an eigenvalue if and only if the vector x has to be non-trivial. Has to be non-trivial. In other words, the vector x can't be the zero vector if zero is an eigenvalue. Well, that would only happen if the matrix A is not invertible. If the matrix A is invertible, then the vector x would have to equal the zero vector. Therefore, if the vector x is not equal, if the vector x is an eigenvector, by definition it can't equal the zero vector. That means A is not invertible. And therefore, 0 is an eigenvalue of A if and only if A is not invertible. Okay, that's a useful thing to know. Okay, are there any questions on that? Okay, All right. Well, let's do a few more useful facts here before I set you off on some classwork here. It turns out that if you have different eigenvalues, then the eigenvectors corresponding to those eigenvalues are going to be linearly independent. Now they prove that below, and I won't go through the proof, but it's a nice proof for you to look at. Basically, eigenvectors corresponding to different eigenvalues must be linearly independent. Okay, and you might intuitively see that, but they prove it below. Another thing too that's important. Okay, another thing also that's important has to do with eigenvectors and difference equations. So you can have, I mean, if you have A times the xk vector, that by definition is the xk plus 1 vector. So like for instance, if I go back to the whiteboard here, if you remember from section 4.9, okay, section 4.9, okay, we have a migration matrix times some initial population distribution, I should say. If we multiply m times the initial population distribution, we're going to get x sub what? What are we going to get? We're going to get x sub, what number is going to go here? Well, what is multiplying the initial population distribution by the migration matrix M tell you? It gives you the population distribution after how many years? Maybe look at your notes, look back to your notes from Monday. That's right, Benjamin, 1 year. 1 year. Now, if I want to find the if I want to find the population distribution between the city and the suburbs after 2 years, I would take the matrix M and multiply it by what vector? How would I find the population distribution? That's right. You would multiply it by the population distribution after 1 year. So you see there's a pattern here. There's a pattern here. In general, the population distribution after k plus 1 years or weeks or, you know, days, months, whatever, the population distribution after k plus 1 units of time is going to equal the matrix A times what? Times what vector? What am I going to put here? Don't be afraid to answer. I mean, I'm seeing a pattern here. I'm seeing a pattern. Yeah, okay, it's a migration matrix M, but that's a matrix, right? I'm seeing a pattern here. I mean, let me ask you, x sub 3 would equal m times x sub 2, right? And that's right, Lewis. So x sub k plus 1 would equal a times x sub k. And that's for k equals 0, 1, 2, and so forth. Okay, so are you comfortable with this concept here, this formula that I've written? Okay, all right, all right. Thank you, Lewis. Thank you, Lewis. So that's you're gonna have a problem in your homework dealing with that, and I just wanted to show that to you. Let me just see here. Yeah, I'm gonna stop there on that. Are there any other questions before we on section? We basically covered section 5.1, I think, pretty well. Okay, I'll stop the recording then. Eleanor's good. Thank you. Everybody.